It makes it.
Good morning, everybody.
Good morning.
Jump right back in. There's got a lot of stuff to talk about today. So.
Going too fucking fast.
Right. Let me see. We got 28 out of 39. We can roll. All right. So we left off. Well, first of all, are there any questions about what we talked about on Friday before we jump in? Because I know we're kind of covering topics.
We were on 1.64, right?
Yeah.
Or 1.7?
Yes. No, you're right. 1.64.
Okay.
Yeah, we're going to work through a couple of more of those examples, some of the more complicated ones. And then we're going to touch a couple in 165 and 166, and that's going to help us with distinguishing between skeletal and Lewis forms and condensed forms. Yep. So let's do that. And I'm going to cut out the next problem because I think this is where we left off, right here. And I think that we talked about the skeletal form, and in the skeletal form, you don't have to show the atoms in the backbone. Anything that's attached to the backbone, then we show it, right? Especially if it's not a carbon. If it is a carbon, you can show it or not show it. You just have to draw a line, and at the end of that line is understood to be a CH3. Let's pick another one, and that way we can talk about all the concepts all at once. So let's do C for now. So I'm gonna highlight it. We're gonna do AC, and we're going to do E. And let's do F. So let's do C. C is given to us, and let me put the date. So what you see right here for C is given in the condensed form. Do you see how you have the groups in parentheses here with a subscript? That's telling you that there are 3 CH3 groups attached to that carbon to the right of it, right? And then this is also a way to condense it. It's telling you that there are 5 CH2 groups. So that's a chain between that carbon and the other CH3, right? And then the CH3 is attached to the last CH2 group in that chain, right? So let's write that out. So let's write it out in Lewis form. So here's that carbon, and we're going to put the CH2s in first. So that's 5. Do y'all see that? 1, 2, 3, 4, 5. And each one of those is a CH2. We're okay with that?
I have a question.
Go ahead.
How did you know there were 6 carbons?
How did I know that there were 6?
Yes.
Okay, so I'm starting from here. Let me get a different pen. And I'm starting from right here, right? and I'm looking at we're starting there first, and I'm looking at here. And that subscript 5 right there is telling me that there are 5 CH2 groups. So 5, that's a 5 carbon chain connected to that C that I have circled in red.
So you don't count the CH3s at the end.
Well, we haven't gotten to those yet.
Oh,
I just wanted to draw the chain out first.
okay.
All right. And then on the other end down here, we're going to put in the CH3. And I'm going to write the hydrogens out. We're okay with that? And then on this end, we're going to write out all of the CH3s, right? So this is the Lewis form of that condensed form. Right? Are we okay with that? It's really important to be able to go between them and understand like the notations in the condensed form. So the parentheses means that that's a group of substituents or a group of carbons. So you can group those carbons up like that by putting the parentheses in. And we'll take a couple from the skeletal back to the condensed, just so you can see the difference. But you can see right here, this is the 5 CH2s. So you see 5 of those there. This is the 3 CH3, the carbon with 3 CH3s attached to it. And then down here, the CH3 was just written out by itself anyway. All right, go ahead.
On the left-hand side, why did you write H3C instead of?
Oh, right here?
Yes.
It's just a convention, and I'll show you. So hydrogen, you know, it can only form one bond, right? So if I write CH3, there's a potential to think that it's the hydrogen that's attached to that carbon next to it, right? So it's just a convention to show that it's the carbon that's bonded and not the hydrogen.
Okay, thank you.
Mm-hmm. Great question, though. I get that question a lot, by the way. So that's a really good question. All right. So now we're going to take this and convert it into skeletal form. What do I need to do first before I turn it into skeletal form? Anybody remember from Friday?
Would it be see what the longest chain is?
Thank you. Who is that?
Nadia.
Good. Very good. We found the longest chain. Here is going to be the longest straight chain. All right. Let me get a different color highlighter. All right. We can see right here is 1, 2, 3, 4, 5, 6, 7, 8 carbons. And for those of you who are thinking, you know, well, why can't I start here? You could. You're still going to get 1, 2, 3, 4, 5, 6, 7, 8 carbons. So the longest chain is 8 carbons. And by the same token, you can start on the bottom if you chose to. 1, 2, 3, 4, 5, 6, 7, 8 carbons. Right. So we're just going to start at the CH3 that's highlighted in pink, because that'll give us a chain, just a straight chain. Right. So when I'm drawing the skeletal form, there's 2 tricks or 2 rules. The first rule is that it has to be in a zigzag to reflect the geometry, right? So you can't draw it straight like that. You can't just draw a straight line, right? You have to show the geometry, the tetrahedral geometry of carbon. So you're gonna draw it like this. The other convention is more of a trick than a rule. It's always one less stroke, right? So if I have an 8 carbon chain, then I'm going to do 7 strokes, like so. If I do 8 strokes, then that's going to give me a 9 carbon chain. So that's just a kind of a trick, right? So you can see right here. Let me point out the 8 carbons. Right, this is 1, 2, 3, 4, 5, 6, 7, 8. Do y'all see that?
Yes.
All right, and then if I go from 1 to 2, let's look over here. Right, this is 1 and that's 2. What's on carbon 2 that I need to include in the skeletal form?
CH3.
2 of them. Is that right? Got 1 here and 1 here. So over here on the skeletal form, I know there's going to be a desire to draw it like this, but that would be wrong, right? If it's in skeletal form, you're going to put those 2 CH3s right here, just like that. Because again, the carbon is a tetrahedron. That's the geometry. So to keep the geometry, you're going to put those groups in just like they're shown right there. And you could leave it like that because the end of every line is a CH3, or you can write them in. It doesn't matter. Questions about that? So we went from condensed to Lewis to skeletal. And then you can see again right here, these are those 5 CH2s that were in parentheses like this in the condensed form. Sorry about that. Right, this is your CH3. And this is your C with 3 CH3s attached to it.
I have a question.
Go ahead.
Can you scoot over to the left? Like,
Yes, over to here.
yes, I have a question. Okay,
Go
so
ahead.
I understand why we drew in the 2 CH3s, but
Mm-hmm. You thinking about the third one?
yeah, why didn't we do the third one?
Well, it's right here, right? This is the third one. Let me get a different color pen. This is the third one right here. But since it's in skeletal form, the termini, I can show it or not show it. Now, but if I showed it, I would have to show it on both ends. So you want to do that?
Yes.
Would that make you more comfortable? All right, so let's draw it in. So this would be a CH3 right here. And then also on this end would be a CH3. Right, the only thing is when you draw a skeletal form, that's optional to show if it's a terminal carbon, meaning if it's the end of a chain or a line, we can show it or not show it. So you can draw it like that, or an alternate way would be to draw it like this, with none of the CH3 shown.
Okay.
Mhm.
On the top version of the skeletal drawing that you just did, how do we know that's a terminus for just looking at it? Because I would think it's like a CH2 or something like that.
Well, let's think about it. All right, that's a great question. If it's a CH2, shouldn't it have a charge? Because if that carbon on the end only has 2 hydrogens on it, it only has 3 bonds to it. So we go back to our initial rule about carbon, which is that it always has to have 4 bonds. Is that right?
Yes.
So that's how I know it's a CH3, because in order for it to be on a terminus and it doesn't have a charge or a pair of electrons, it's got to have 4 bonds to it. So this is 1 bond to it right here. The other 3 bonds are understood to be hydrogen.
Okay, thank you.
Yep, that's a good question. All right, any other questions about that one? Let me add a page so we can do, I need to add a page. Let me just move this down. All right, other questions about that?
I have one more.
Come on.
Can you zoom in, please? Okay, so for the 5 carbons, like,
Yes.
and okay, so since we didn't draw the hydrogens, it's understood that they're already there, right?
Yes, yes. Everywhere you see a vertex where two lines come together, it's understood to be a CH2, unless you have another atom or atoms or a group of atoms attached, like on the end with the two CH3s.
Okay.
Yeah, there are no hydrogens on that carbon because it will have too many bonds to it.
Okay.
But anywhere you see a vertex coming together and there's no other atoms attached to that vertex, the two other atoms are understood to be CH2s.
Okay.
Yeah, great question. Anything else on that example? All right, let's do another one. Which one do y'all want to do? You pick. We're going to do both E and F. Which one do you want to do?
E.
E. All right, let's do that. Let me just copy it. Let me see where I can put that. I'm gonna just put it on. All right, can y'all see that?
Yes.
So with rings, if you have a ring, there's really no way to write a condensed form for the ring, but we can go from the Lewis, which is what this is, Lewis form. We can take that down to the skeletal form, but for a ring, there's no way to write a condensed form. So with that ring, how many carbons are in that ring? Let's count them. 1, 2, 3, 4, 5, 6. Right, those cyclic structures like that, we call them cycloalkanes. Right, and those 6 carbons would be a hexagon. Right, if I had a 5-carbon chain or 5-carbon ring, it would be a pentagon. If I had a 4-carbon ring, right, it would look like a box like that. If I had a 3-carbon ring, it would look like that. Right, can you see that? That's 1, 2, 3 carbons. That's 4 carbons, 5 carbons, and then 6 carbons. I could also have a 7-carbon ring, which will be a heptagon. 1, 2, 3, 4, 5, 6, 7, so on and so forth. So those cycloalkanes have a definitive like shape, right? And I'll put it down here, 6 C's. I think in the video that I sent you on skeletal and line forms, I think I had something in there about rings and the different shapes of the rings. So that compound up top, limonene, is going to have a 6-membered ring like so, right? And then attached to that ring, we're going to have a double bond, which looks like this. And we're going to go back and explain everything too. And then on the other side, right here, we have a methyl group. All right. Questions about that? So this is the skeletal form for limonene, right? Oh, I'm missing something, Emma. Arna. You see what a CH3 group is? The carbon is connected to. What am I missing?
Which one?
Right here. That's a double, sorry. That's a double bond, isn't it?
Yes.
So I need to show that down here. So this, because it has a double bond inside the ring, we call it a cyclo-L. We're going to talk about functional groups too. Cycloalkene instead of alkane. Right, it's a cycloalkene. The suffix changes because the double bond is present. But we'll talk more about that later.
I have a question.
Go ahead.
Since the double, so like, okay, why did you draw the double bond on the skeletal form where you drew it? Like,
Oh, I can't get rid of that. If I didn't have the double bond in there, this would be a whole totally different compound.
right, but like, does it?
Why
Why
that's
did you
why
draw it right
inside
there?
and not outside? Is that what you're asking?
No, like, why didn't you draw it diagonally under, like, underneath where you drew it? Like, does it matter? I'm asking, like, does it matter where the double bond is?
Oh, yes, it does. If you look up here, you see how the double bond is here between these three atoms?
Yes.
So down here, wherever my CH3 is, which is right here, right? That double bond has to stay in the same place. It's got to be there. I can't put it anywhere else.
Okay, thank you.
Yeah, it's got to be identical to where it is in that Lewis structure. That's a good question. So are you're asking why didn't I put it here or here? Is that right?
Mm-hmm.
Yeah, it has to be identical. Sorry about that. It has to be identical to the Lewis form. So it's got to be here. Otherwise, it'd be a totally different compound. All right. Any other questions about that example? So again, you can look here, you can see that there are 1, 2, 3, 4, 5, 6 carbons in that ring. And then outside the ring, attached to it, we'll call this, because it's attached to the ring, we call it a substituent. Right? The substituent is a double bond. And let me change the color here. So you can see that here, here, and here, those carbons are part of that double bond. Now, let me ask a question. At the end of that double bond, is that a CH3 or is it a CH2? And I covered up the top on purpose.
CH2,
It's a CH2. Why do you say that? How do you know that?
because the double bond takes away 2 of the bonds that it can make.
Yes. Yes, the double bond takes up 2 spaces on the carbon, so there are only 2 spaces left. So it's got to be a CH2, right? I'm asking that question because that's a common error that I see when students draw skeletal forms, or even when we start working with reactions of alkenes. You know, students make that mistake of thinking that at the end of that double bond is a CH3, and it's not. It's a CH2. What about on the other carbon in the double bond, on this one? What do you think?
CH3.
No, the one I'm pointing to, that's in the
Okay.
double bond. Are there any hydrogens on that carbon?
No.
No, because it already has 4 bonds to it. Are y'all following that? What
Yeah.
about here? Go ahead.
Actually, I see it. Never mind.
All right, what about here? Any hydrogens on that carbon?
Yes.
Yeah, 1, right? Because you can see that carbon has 3 bonds to it already. It's got a double bond. Let me get a different color pen. It's got a double bond, so that's going to take up 2 spaces, and it's got a bond right here, so that's taking up 3. The 4th space in a skeletal form, if it's not shown, it's understood to be hydrogen. All right. What's the hybridization state of that carbon that I just pointed to, the one right here?
SP3.
If it was sp3, would it have a pi bond to it?
Is it SP2?
It's sp2. Yeah, if it was sp3, it would have all single bonds, and it doesn't, right? Or all sigma bonds. It has 3 sigma bonds and then the pi bond. Now, what about this carbon? The CH3 that's hanging out here. What's the hybridization state of that carbon?
SP3.
It's sp3. Good. What's the hybridization state of this carbon that's in the ring?
SP3.
sp3. It doesn't matter if it's in a ring or a chain. If it's cyclic or if it's acyclic, it does not matter. The hybridization state is what it is. If it has a pi bond to it, it's either going to be sp2 or sp. If it has no pi bonds, it's going to be sp3. I just want to throw that in there just to make sure we don't forget that. All right, we good? Everybody good on that example? Here. All right, let's do the other example from up here. And then we're going to go and do, we'll zip through a couple of the other ones. Where am I? Here we go. So we did A, C, E. Let's do F. F looks like a beast, but we're going to tame it. That's what we do for a living. Tame the beast. All right, let's go here. And let me do something real quick. All right, so let's see if we can break this down like we did the other one, right? We see we have a CH3, which is going to be a terminus. We're going to convert this to line form and then skeletal form. On this end, we got a CH3. Now, in this example, right there, a lot of groups in parentheses. That's on purpose, and I'm going to explain it. So right here, you see how this carbon next to it is a parentheses. It's got a subscript 2, and it's got in parentheses, a CH3. What that means, anytime you have a condensed form, the atom to the right is going to be the atom that's bonded, right? So in this form, in this condensed form, that carbon has 2 CH3 groups bonded to it. Are you following?
Yes.
And then to the left of it is bonded to that CH2, one of those CH2s in that group. And then it's also bonded to the CH that's to the far right. So it's bonded here. Uh-oh, wrong pen. It'll be bonded here. And awesome. Here. All right, we'll flush it out when we get into the line form. Same thing with this carbon. Right, it's got a CH3 to the right of it in parentheses. Right, and it's a CH. So if you look at that, that's only 2 spaces. So it's got to have 2 other bonds. So it's also a part of, it's also going to be a part of the chain. Right, and let me go down to here because this is the only place that maybe cause some confusion, right? That BR is bonded to that CH group, right? Because it's to the right of it, right? So let's see if we can draw it out. So let's write out, let's start at the C, at the far left. We're not going to start at the CH3, we're going to start at that C. So we're going to start here, boom, and then we know that that has 2 CH3s attached to it. All right, so this is a CH3 and that's a CH3. And then it's also connected to a CH following that has a CH3 attached to it. Do y'all see that?
Where did we start at?
We started right here. Let me highlight it. We're starting here. We'll add the other part in after we build out the rest of it, because this part of the chain has a lot of substituents attached to it. So we'll build that part out first, and then we'll come back add that last piece in. All right. So now next to that is another CH, which is right here with a CH3 attached. And then next to that, same thing, a CH. It's down there with a BR attached. And then a CH, we'll draw it out, sorry. CH3 on the end. And then on the to the left of that purple carbon, you have two CH2s. And then a CH3. Right? Anybody not see that? So this is the Lewis form. All right, yes, no,
Yes.
So is it best to go, like, we had the starting point and then we just basically went right? Is it
yes.
best just go finish right and then come back and then go left?
Yeah, for something that's complicated like this, yes, that's the best strategy. Because you see all those CH3s in parentheses, all of those are substituents
Okay,
on the chains, like right here, and then the bromine, all of that's those are substituents on the chain.
okay.
Mhm. Great question. So now let's look at this. Let's see how many carbons we got. 1, 2, 3, 4, 5, 6, 7, 8 carbons in that chain, right? It doesn't, we can count from the substituents, but it's not going to give us an 8 carbon chain, right? If we start counting, let me give you an example. If we start counting from here, 1, 2, 3, 4, 5, 6. Same if we start counting from here, 1, 2, 3, 4, 5, 6. So we see what our longest chain is. It's 8 carbons. Are y'all okay with that?
Yes.
Yes.
So we want to turn that into a skeletal form, right? What would you do? First of all, how many strokes is it going to take?
7.
7 strokes, good. And it's got to be what? Written in a
Exactly.
It's got to be, right? You can't write it any other way because you have to honor the fact that carbon is a tetrahedron. Come on, battery. I just need you for 15 more minutes. Right? So that's 8 carbon. What's the name for 8 carbon chain? Anybody remember?
Octane?
Octane. Very good. That's the parent. All right. So now if you look on carbon 4, so let's count them out. Let me use the same color highlighter. 1, 2, 3, 4. What's on 4? Up here. Let's count it. 1, I have to zoom in. 1, 2, 3, 4. 1, 2, 3, 4. What's on carbon 4 in the Lewis form?
CH3,
How many?
2.
2 of them. So I got to put those in down here. Following? Whatever is in that Lewis form, if it's not in the skeletal form is a different compound. And then what about on 5? What do you see on 5?
CH3.
One CH3, right? And then what about 6? Same thing, right? A CH3. Is that right?
Yes.
And then on 7, you have a bromine. And then each terminus is shown. I can draw it or not draw it. You want me to write out the CH3 or no? Which one do you prefer?
I said, if you write the second one, can you write the first one? Yeah.
Yeah. Yep. All right. Any questions about that example? Right? We can actually, I'm gonna give you a quick, and I hate nomenclature. I'll be the first one to tell you it's the worst part of organic because it's so boring. so many rules, but we can name this, right? We're going to count. When you're doing nomenclature, you actually count from the end on a chain like this. You want to count from the end that's where the first substituent is encountered. 6, 7, 8. Somebody already said it was an octane. Is that right? Because it has 8 carbons in the chain. Right? This is what you call your parent name. And this, I'm not covering nomenclature. I'm just sliding it in here because it fits. Right? So octane is my parent because it's 8 carbons. Where are my substituents? And when I say substituents, those are the groups that are on the backbone, right? Because the 8 carbon chain is my backbone, and everything that's not a part of that backbone, we call it a substituent. What do you see?
Is it,
Bromine, that's 1, right?
yeah.
And then what's the other one? The CH3. Anybody know what that's called? If you watch that video, you should know what it's called.
Is it a
So it's called a methyl. A CH3 is a methyl. I know for certain that was in the skeletal and line forms video, but we ain't gonna harp on that. How many methyls do we have? I have them highlighted in green because every one of those
4.
lines,
4.
4 methyls. Good, right? So we're gonna, and they are at 3, 4, and 5. Is that right? That's the location. Yes, no,
Is it
Yes.
prime?
Yes.
How do you say it?
right? So we got a methyl group at 3, 4, and 5. I'm gonna explain all this once we write the name out, but I'm just giving you a kind of a crash course in nomenclature. Go ahead, Tia.
Okay, like, is it 3 prime, 4 prime, or is it just 3, 4, 5?
Yeah, it's just 3, 4, 5.
Okay,
Did you say prime?
yeah,
Yeah, no, we're not using that notation.
okay.
Yeah, great question. All right, so we have the methyl groups are at 3, 4, and 5. The bromine is at position 2. Everybody agree with that? And we started counting on the end where the bromine is. There's a rule that tells us that that's what we have to do because we want all our substituents to have the lowest number possible. So if I started counting from the other end where the 8 is, bromine would be 7. But if I start counting from the end where it is, it's 2. All right.
Wait, why are we starting from that end? Because I thought we were starting from the other end at first.
Well, that was just to number the carbons, right? We weren't really trying to name it. We were just numbering them so we can know where to put everything. But when you're trying to name it, you got to start at the end where your first substituent shows up. And in this case, it's bromine on carbon 2.
Okay, thank you.
Mm-hmm.
I
So
got a quick question.
go ahead.
Why come we not count the other CH3s on the end?
Because they're part of the chain.
All right.
Yeah, so if they're a part of the chain, you don't count them as methyl groups. They're termini. So it's a terminus on one end and terminus on the other end. So they are a part of the backbone. All right, so let's see if we can write this name out. So you list, so bromine and methyl are your substituents. And you list them in alphabetical order before the parent. So this becomes 2-bromo, right? If you have a halogen like bromine, you have to change that suffix to an O. So 2-bromo, now put a dash between that. 3, what am I saying? 3, 4, 5, 5. We got to put that 5 twice because you got 2 methyl groups. Tetra, because it's 4 total. Methyl. Oh, shucks. Hold up. Let me move this over some. tetramethyl, and then octane, OCT-A-E-N-E. You see how the name is it tells you everything. So the parent, that's the backbone. And then the groups that are attached to the parent, right? Those are my substituents. And then each substituent has an address. I like to think about this like as the parent being the street name, the number being the address, and then the name of the substituent being who lives at that address, right? So street name, address, and then resident. So the bromine lives at carbon 2. We see that up top. The methyls live at 3, 4, and there are 2 of them at 5. And then octane is the street name. I see 2 hands up. Go ahead. I don't know who was first though.
So for the skeletals, just skeletal, we only have to show the CH3s and not the H.
Right, no hydrogens, right? That's the purpose of doing it in skeletal form. You show as few atoms as possible.
Okay.
Right, and you really, in all honesty, the ones that are on the end down here, you don't have to show those. I just wrote them in, but you don't have to show them. All right, that was another hand up. All right, any questions about that example? So we went from condensed to Lewis to skeletal. Is that right? I want you to try one on your own to do the same exact thing. Go from condensed to Lewis to skeletal. I want you to try this one. Right? And if you do it today and get stuck, you can ask about it on Wednesday. Condensed to Lewis to skeletal. All right. We got, let's do 166 because 165 is the same as what we were already doing. So let's do one.
Can you go back up real quick?
Go up to here.
Yes, hold on. Good, thank you.
Mm-hmm. Let's do 166 and let's do, because we only got 5 minutes left, A and C and D. So let me cut that out and put it on the new page. And I'll clean all this up before I post the notes to Blackboard. All right, let's do A right quick. A is an example of, because we're going to talk about functional groups too. A is an example of what we call an aromatic functional group. And so there's a negative charge on this carbon. What does that mean? If it's negative,
It has more electrons.
it's got a pair of electrons on it. Very good. And there's a negative charge. And the question asks us to draw in all the hydrogen atoms and non-bonded electron pairs. So that carbon having a negative charge means that there's a lone pair on that carbon. All right. Now, how many hydrogens are on that carbon?
What?
0.
0. Very good. No hydrogen. Right? No hydrogens on that carbon because the octet is filled out by that lone pair.
Which one? Which carbon?
This the one that we would show with the charge on.
Okay.
Right. If I put a hydrogen there, that carbon will have 10 electrons around it. And that's not possible for carbon. All right, let's go to the next carbon. How many hydrogens on that carbon?
One.
One, good. How many hydrogens on all the rest of the carbons in the ring?
One.
One. And they're all, what hybridization state is each carbon?
SP2.
sp2, very good. Including the one with the lone pair, right? That all of them are sp2 hybridized. Let's look at the, we're at 5% in 3 minutes. I can do it. Let's go ahead and look at, sorry about that. Let's go ahead and look at B, because that'll give me a chance to introduce another functional group. All right, so for B, that carbon has a negative charge on it. This is a functional group that we know, what we would call a ketone. We'll come back to that. We're gonna go through all the functional groups. The best way to learn them is to memorize them. And there's some classes like carbonyls, and then alkyl halides, alkanes, alkenes, alkynes, but we're gonna talk about all that, so don't panic. And we may even end up pushing the exam until we get like that stuff covered, but that's not set in stone yet. All right, so how many hydrogens are on this carbon right here? It has no charge, it has no pi bonds to it. How many bonds should it have? Good. There are 3 hydrogens. This is it's a terminus, so it's actually a CH3. So there are 3 hydrogens on that carbon. Very good. What about the one here with a pi bond to it?
0.
None. Good. No hydrogens. Sorry about that. Right. And then over here, this is a carbon. Wrong pen. Right. How many hydrogens should be on that carbon? It has a lone pair. It has 1 bond to it on one side. How many hydrogens does it need?
1.
2.
2.
2 hydrogens. Great. Right. Otherwise, if it only had 1 hydrogen, it wouldn't have a negative charge. Right. Because remember, it's valence minus actual, how we calculate that charge. All right. Then it asked us to put all the lone pairs in. Non-bonded electron pairs. So for oxygen, how many lone pairs should I put on oxygen?
2 lone pairs.
2 lone pairs, 1 here and 1 here. Are y'all following that? Do y'all remember that from part 2, G-Chem, when you did Lewis structures?
Yes.
Okay, great. All right. All right, let's do C, and then we'll stop. We got to stop at C. This went a different way today. I intended to talk about other stuff, but that's fine. I just want to make sure you get the fundamentals first, because if you understand formal charge, skeletal and line forms, where to put lone pairs, and how many hydrogens to put on a atom that has a charge or doesn't have it. If you understand those fundamentals, then when we get to the harder stuff, it's going to make that stuff a lot easier to comprehend. All right, so I'm not really worried about, I'm not rushing so we can take the test Friday. We can push the test if we have to. That's not a big deal. Let's do this, right? How many hydrogens are on this carbon?
1.
That's written as a skeletal form too, so
1.
1 hydrogen, good. What about here?
2.
3.
3.
It's 3, right? It only has, that carbon only has 1 bond shown to it, so it's understood to be a CH3. But remember, it's a terminus, so if it's a terminus, or the end of a line is understood to be a CH3. Now this carbon has a plus charge on it, right? What does a plus charge on a carbon mean?
Means that there's less electrons present.
Yes, it's electron deficient. That's exactly right. So if I write that out as a carbon, how many hydrogens do I need to add to that to make that formal charge add up to +1?
2.
Just 2. right? So it's two hydrogens on that carbon and it has a +1 charge. All right, are we okay? Everybody following? Can we do D real quick without having to sketch it out? How many hydrogens on each one of these carbons in this pi system?
One.
One each. Good. That's excellent. There's a hydrogen on each one of these carbons. Because remember the golden rule, right? Carbon only forms how many bonds?
4.
4. What about here? How many bonds does it have to it that you can see?
3.
3. Good. So the 4th bond is understood. If it's not another atom, it's understood to be hydrogen. And we know that this is a what? Because we've done 3 of these already. It's the end of a line, so we know it's what?
Substituent.
CH3.
A CH3. Right? And then on this last one right here, where the plus charge is, how many hydrogens do you think? How many bonds can you see?
We can see 2.
You can see 2. And you know it, if in order for carbon to have a plus charge, it's got to have
So just one on there?
3 bonds, right? So there's 1 hydrogen attached. I didn't mean to cover up the positive. All right. So we're gonna keep pushing with these concepts. What I'm trying to do is kind of layer everything together, right? So I'm not just teaching one thing at a time, because then we could be talking about Lewis and line forms for the whole semester. So I'm trying to layer in formal charge, trying to layer in Lewis and line, and layer in like hybridization and all the other concepts, because everything in this class is like Lego. It just one concept just builds on the other. So we're gonna pick up on Wednesday. I'm gonna clean these notes up, and we're gonna run through some formal charge, and then we're gonna start talking about polar covalent bonds, electronegativity, dipoles, and things like that. And then on Friday, we'll probably start resonance, and we'll make a decision on Friday whether or not to have the test Friday or to move it to Wednesday or Friday of next week. We're good with that?
Yes. I had a question.
Go ahead.
Are we supposed to do the post assessment at the end of each module?
No, you do that right before the exam.
Okay.
Yeah, good question. All right, any other questions about anything? All right, if not, we're gonna log out. I'll see y'all on Wednesday, God willing, and have a great rest of your day.
Thank you. Have a great day, sir.
Thank you.
Okay.
Everyone, sir.
Thank you.
You too.